Seen a few different videos now with our infinite series, and we've just begun to determine, do these series converge or diverge? So one of the easiest ways to be able to tell if it converges and then to actually get that value of convergence, or what the sum is the geometric series. There are some other tests that we're going to look at in the coming videos, or several other tests, but one of the easiest ways to tell if the series diverges is the nth term test for divergence. This is always what I start with. Start with by thinking about, does this sequence converge or does it diverge? And if the sequence diverges, then right away we know that the series also has to diverge. So just to put that into words, the nth term test for divergence states the summation from n equals 1 to infinity of an diverges if the limit as n goes to infinity of that sequence fails to exist or does not equal 0. So right away we can tell if something diverges. Now I do want to stress that if the limit of the sequence does equal 0, that does not mean it converges. All that means is that the nth term test for divergence fails. We need to go on to test for convergence in another way. And we're going to see an example of that. So let's just start with some basic examples. So let's take the summation from n equals 1 to infinity of -1 to the n. So what I'm going to do is I'm going to look at what happens to the sequence -1 to the n. What's going on with that sequence? And this does not exist. We've looked at this in the past. We looked at this with sequences. We have this alternating number where it's going from -1 to +1, -1 to +1, never reaches a set value, so the limit fails to exist. Therefore, using the nth term test for divergence, sometimes called very quickly the divergence test, a little bit more concise, we know the summation n equals 1 to infinity of -1 to the n must diverge. So this is something that I want to see more and more of. When you're writing whether something converges or diverges, you're doing the work to find out, what's true about this series or this sequence, but you're also describing to me using what test you have used to actually test the convergence or divergence. Don't just say this thing converges or this thing diverges. Show me why it converges and diverges and state that test that you're using. And then as we go into additional tests, we're going to see that we have to have certain conditions are met in order to use a test. We kind of did this with the integral test and the, sorry, not the integral test, I'm getting ahead of myself. When we're testing the convergence or divergence of integrals, we used the comparison test, the limit, and the direct comparison test. And so for those, we had to show the conditions were met first. So we'll see more of that in later videos. Let's take another example for now, though. Let's take the summation n equals 1 to infinity of 1 minus 1 over n. So I'm going to take the limit as n goes to infinity of 1 minus 1 over n. And so if we were to let the n go to infinity, what we see here is that this portion right here, I'll highlight it, that is going to 0, because we can really break this up into two limits. Remember, if we want, we can have limit of 1 minus the limit as n goes to infinity of 1 over n. So this second portion is going to 0, but the first portion definitely goes to 1, and so we have 1 minus 0, which is 1. And so because that is not equal to 0, we can state, using the nth term test for divergence, the summation n equals 1 to infinity of 1 minus 1 over n diverges. So it's not strictly saying that the limit doesn't exist. It could be that the limit exists, as it did here, it's just not equal to 0. So that's another example where the series will diverge. Let's take another example. Let's say we have the summation n is equal to 1 to infinity, 3 times n squared over 2n. And so I'm going to consider the limit as n goes to infinity of 3n squared over 2n. Well, we can simplify this thing if we want to. 3n over 2, and very clearly we see that that is going to infinity, which means the limit really does not exist. Infinity is just another way of saying that the limit doesn't exist. And so the summation n equals 1 to infinity of 3n squared over 2n diverges by the nth term test for divergence. Now I'm going to again stress what I stated earlier in this video, which is that if we show that the series, the sequence rather, the limit of the sequence does go to 0, that does not prove convergence. The nth term test for divergence will never prove convergence. It only proves divergence. It's right in the name. Never tell me something converges using the nth term test for divergence. And let's see an example where that would be true. Let's take the summation n equals 1 to infinity of 1 over n. So if I try to apply the nth term test for divergence, I take the limit as n goes to infinity of 1 over n. Very clearly that is going to 0. All that tells me is that I need something else. I need to use another test, or we're going to think about this when we're going to write out its terms and look at it. So we can never use the nth term test to show convergence. Really, really important. So let's think about what this series would look like. We'd have over n, we'd have 1 over 1, which is 1, then we'd have 1 over 2, a half, then we'd have a third, we'd have a fourth, fifth, a sixth. We're just going to keep going. I want to write out quite a few terms so we can really see what's going on. And I'll hold off for now, right? There's obviously more here. So let's take a look at this. We're starting off with a 1. We're adding a 1/2 to it. Then a third and a fourth, that would be a little bit greater than 1/2. We could find its exact value. This would be 4/12 and then 3/12. That would be 7/12. 7/12, a little bit greater than 1/2. And that 1/2 is the key there. I'll come back to that. Let's look at these next 4 terms. We could again add these, and so we'd have a common denominator of, what would it be? 8 times 7 times the 3 times 5. It'd be a really large common denominator. We'd get it, we'd find out that this thing is once again greater than 1/2. And we could keep doing this, right? For all these later intervals here, we just keep adding something greater than 1/2. And that number keeps going up and up and up. So this next one would be 8 terms that we would need. The next 8 terms, that would be greater than 1/2. And then we'd have the next 16 terms. That would be greater than 1/2. The next 32 terms, that would be greater than 1/2. So we're definitely going to 0. These things are getting smaller and smaller. But what we see that we're doing is we keep adding 1/2. Now it takes us a lot longer to add 1/2 each time. Right? It took us 2 terms, then it took us 4 terms here in red, then it took us 8 terms, then it took us 16 terms. But over and over again, we just keep adding 1/2. And so if we continually add 1/2, well, that's clearly not converging to a single number. If we just keep adding a half, this thing is getting bigger and bigger. It's going to infinity. And so this one diverges. This series is known as the harmonic series. Harmonic series 1 over n. We can see that the sequence, the limit of the sequence was equal to 0, which told us we couldn't use our nth term test for divergence. However, when we actually went to find that series value, when we went to find its sum, we saw that it still diverged. That's the important point here, is that the nth term test will never prove convergence. Anytime you see 1 over n, that is the harmonic series, and that is always going to diverge. And that's going to be important as we move forward, because we're going to use some comparisons, like we did with our limit comparison test and direct comparison test when we were studying integrals. When we had those indefinite integrals, we're going to use some comparisons, and so it's nice to have something we know diverges to be able to compare off of. Now, we already have the geometric series as well, so we can compare based on the geometric series. But this gives us something else to compare. And then the divergence test gives us that nice, quick, easy way to see, does something diverge, or do we need to go on to find another test? I think it's always a good idea to start with the divergence test. From there, if it diverges, great, you're done. If it doesn't diverge, well, then we've got to find something else, and that's what we're going into next.